All right, so there is a quiz today. The password is complex, all smaller letters. So do make sure that you take that. Is there any questions about any content up to this point? Yeah?
Did you say you posted the solution for the exam?
Not yet.
Oh, okay.
Sorry. I will be, yes. Yes, I hope to do it by tomorrow. So yes, I'm going to do exam 1 solutions and exam 2 solutions since I forgot to post exam 1 solutions. So
Is that 2B?
the first exam I'll do 1A, 1B, and 1C solutions for that one too. And I still have not been able to get up Unit 3 practice problems, but they should be available also tomorrow. So yes, please go through the solutions. Make sure you do understand anything that you may have missed. And if you have any questions, I guess let me know. Any other questions, comments, concerns about any of the material? So I mistakenly said that we had done all the content for this next exam, and I was mistaken. We're going to do a small little section in chapter 12, and so if any of you are interested, you can look at that. We'll go over that on Friday. What we're going to do with that one is that we have looked at specific frequencies for omega, and in chapter 12 it talks about using that S variable and solving the circuit in terms of S, and then we can actually look at S in a generic form instead of just one particular omega. We can actually solve the circuit and then look at, for varying frequencies, what does our responses look like? And so that's the last topic we'll talk about for the content of this next upcoming exam. So it will just be, I think it's 12.1 and 12.2, so that's the only two little sections that we'll talk about in there. All right, so I will update the Canvas page to also include that for reading. So it will include chapters 12.1 and 12.2. So just add that into your reading, and then I'll add some support information for that one too. All right, so today we're going to do more examples. So transforming the circuit into the phasor domain, analyzing that phasor domain for something such as the Thevenin equivalence. With that, you may need to use node voltage, Ohm's law, KVL, KCL, etc., superposition to be able to get to that solution. The other thing we want to talk about is the difference between S and J omega. I'm actually going to start with that one. So S versus J omega. So S is actually the root of a system. And so you can kind of think about this as more of a general form. And J omega is going to be a specific frequency. So when you think about a solution to a system, S is, both of these are complex. So meaning that they're in the frequency domain. And when we look at a specific S value, it would be one particular solution, and a root could be like a point such as this. This is going to be a rectangular form would be written as A plus BJ, or A, B minus A, I guess, but minus A plus BJ. And so it has both a real form or real component and an imaginary component. here we see that j omega is only the imaginary component. And so when S equals j omega, this is going to actually be the steady state solution. The other thing that's different about this is that the S is for Laplace and the j omega is for Fourier. So this S equal to j omega is converting from Laplace to Fourier. And so you can do that in the time domain as long as you're just looking at the steady state condition, which is most of the time what we want to know, is that steady state response. So with that, we can then describe this as 1 over CS, and this as just SL, and this is still going to just be an R is just an R. So when we analyze the circuit and we want a little bit more generic form, we can just use the S instead of the j omega. So this means that we won't have a specific value for omega, and we just use that S variable. And so a result would be that we would get like Vx, and it would now be in terms of S instead of the j omega. And so this is very useful when you're looking at a little bit higher level of the system, and then also when we want to look at, well, what happens as we have a range of frequencies instead of one specific frequency. So this is basically what 12.1 and 12.2 is going to talk about, is how do we look at these equations now with just an S variable. Okay. Any questions on S and j omega are pretty much then interchangeable, again, just as long as we're talking about the steady state. So when I talk about them and say, oh, we can just use the S variable to solve the circuit, or we can just use j omega, they mean the same thing for frequency. Does that make sense? Okay. All right, so let's go back to, this was 7.34. We did last lecture A and B. So today let's work on these three. So we're just trying to find the impedance equivalent from these two, between the two nodes of each of these. So C, D, and E, and go ahead and convert them based on the specific omegas. So for Z3, you're looking at 10 to the 6th as your omega. Z4 is 10 to the 5th omega, and Z5 as 2000.
So if you like if you solve one of these and substitute it, it's still not like a unique equation, so you're still always gonna have to have like no voltage, so. So since the voltage is given there, then you still always gonna.
What is this for the different number?
This is what the number is in order to buy.
Right now, we're looking at the same.
Oh, okay, so we don't do anything with it.
3,500. So they're gonna be the same for our inputs right now.
Okay.
And then they'll be a little different when I talk about, well, we don't even know what the input is. We're gonna use that as a.
Okay, but like, these balls that they have from the goes into the current source and the voltage source, which is now.
Well, it's whatever the sources are.
Oh, okay.
And in this case, your sources have to have the same frequency. They can have phase shifts on them, so they can be phase shifted between each other, but they have to have the same phase frequency.
So they begin with phase shift.
Yeah, so if you have different phase shifts, here you have no phase shift, and here you have a phase shift of -30 degrees off of power. So these are the same frequency, but one's phase shifted to the other one.
Okay, so.
Yeah, because you know, it's asking if it's
Let's go with these numbers.
series will be treated by.
So here, why is it just these two ones? Just like you say here. So we say these
All right, so for Z3, if we are still not seeing fully that things are in parallel or series, again, I suggest making sure that you highlight the nodes. And then hopefully from this, you can see that the 25 nanofarad is in parallel with the 30 ohms. So you're going to want to put these two in parallel. And then you would have these two in series, and then those two in parallel would then also be in series with this. So I'm going to call this Z1 or ZC1, ZC2, and this would be 50 plus ZC1 plus ZC2 in parallel with 30. And ZC1 is going to be a minus J over 10 times 10 to the 6 times 20 nano, which is 10 to the minus 9. So this ends up being 20 minus 50J. And 2 is going to be a minus J 10 to the 6 times 25 times 10 to the minus 9, which should be minus 40J. You guys get minus 50J and minus 40Js? Okay, good. And so this is then 50 minus 50J plus a minus 40, or 1 over minus 40 plus 1 over 30. And then this ends up being 69.2 minus 64.4J. And again, what's the units, even though we have complex, what are the units here? Ohms, correct. So this will be my rectangular form for Z3. What does this look like component-wise? It's an R, correct? What's this one? Faster, correct. So it would be a resistor in series with a capacitor. Is that equivalent C3? Okay. All right, any questions on that one? Yes, people got it? No people got? Yes, I got several yeses. Great. Okay. Z4. So D. We have these two in series, these two in series, and then both of those are in parallel with each other. So this one is going to be, I'm going to call this 3 ZL1 and Z4, ZC4. So 4 is going to be 10 plus Z3, C3, it's hard to say, and then 10 plus ZL1 in parallel with ZC4 plus 10. And ZC3 in this case is 10 to the 5th is now omega. So a minus J 10 to the 5th times 0.5 times 10 to the minus 6 for micro. And that ends up being D minus 20J. And ZL1 is 10 to the 5th times 0.1 times 10 to the minus 3 for milli, and that's 10J. And ZC4 is a minus J over 10 to the 5th times 1 times 10 to the minus 6. And that's a minus 10J. So ZC4 is 10 minus 20J plus 10 plus 10J. Let me do them all over. 1 over 10 plus 10J plus 1 over minus 10J plus 10. And this ends up being 20 minus J20 ohms. Yes.
I have a question about how you went from like the air buffer of like 1 over whatever to the 20 less. Like is that using a calculator?
So from there to there?
No, from there to the answer.
Yeah. From this equation to the answer? So this depends on your calculator on how you're gonna do this. So you just have to make sure your handheld calculator, you know how to use it to do this one. So, for mine, I can just put it in that form with the parentheses, correct? And it will come out. I don't know if that answered your question or not. Is it not coming out that way for yours?
I just didn't know how to input it into my graphic calculator.
Again, it depends on your model of calculator. What do you have? TI-84.
There is an I button.
Anybody else have any suggestions for TI-84?
Yeah. There's an I button if you do second tier.
You found the I? Okay, anybody else have questions about their calculator? Wants to see if anybody else in this has already figured it out? Okay, so do make sure you know with your handheld calculator, because that's what you're going to use on the exam, how to be able to calculate expressions such as this. All right, did you guys get to Z5 yet, or still working on that one? You guys got, some others are saying yes. Okay, so E, on this one, as I highlight the nodes, I see that the 30 and the 20 micro are in series with each other. And those two are in parallel with the 10 millihenry. And once I combine all that as one, it's going to be in series with the 20. And then I'm going to have that the 50 micro is in parallel with that branch. So Z5 will be 10 plus the 50 micro, I'm going to call that C5, ZL2, and this is ZC6. Okay, so then it's ZC5 in parallel with all of those. And that was 30 plus ZC6, which is in parallel with ZL2. and that's added to the 20. And there's two of them. Okay. So ZC5 is a minus J. Omega in this case is 2,000. Times 50 times micro, which is 10 to the minus 6. And that is 50 micro, oh wait, sorry, minus J10, minus 10J. And then ZL2 is 2,000 times 10 times 10 to the minus 3 for milli. And that's 20J. And ZC6 is a minus J over 2,000 times 20 times micro, which is 10 to the minus 6, which is 25J. So this all written out is going to be 10 plus 1 over a minus 10J I'm going to call this something else because it's a little messy. I'm just going to call that Z5, and Z5 is 1 over 30 minus 25J plus 1 over 20J. So 1 over Z5 plus 20. And this ends up being 12.67 minus 10.98J. All right, so quiz today, the answers are to put in these values, so do use those exact values in the answers for the quiz from today. All right, questions about this? Okay, again, making sure that with your calculator, you're able to get these results. Okay. Good on Thevenin? Resistances or impedances? Okay. All right. Okay, so let's go back to a full circuit. You're given that your input is 12 cosine 10 to the 4th t, and you want to first find, well, let's just do the other one. I'm going to erase this one. So let's just find the Thevenin equivalent between C and D. And then from there, we'll find I of t. Okay, so find the Thevenin equivalent first. Between this C and D node.
but it does everything at once. Like, I've worked from folder to work together. That's fine, yeah, that's fine, bring it on. Oh, really, you find it, like, I get it. He's in bed. No, that's the same calculator with second 26. Is it the phone? Oh, yeah. I know, right? It's like, who wants to be thank you? This one? Yeah, let's look at HCP together. I think that's it. Oh, yeah. I've YouTube the whole video. That's what I always do. So, what I wanted to do today, like, does it do that?
So you can use like but it'll be able to convert it to states to like
What about you?
you would still have to like factor like she did or is that what you want, but you have the VX factor that and then you solve for VX. But when you finally get your final answer, then you just like test it. So you would just like say like, this is VX is equal to this. So you just type this out, divide by this. Well, you can do that. Then you would just have to, I mean, if you were to assume it like, if you just loaded it in this one with one side, that is, you don't need. I understood. What if you just leave it like this? positive for isolation. To the battery, the current should be positive. It's based on this is, or does it, yeah, does it open?
So Vx minus 2, but I always describe it this way. So if Vx is 1, 1 minus. So this way it would be 0 minus a minus 2. Yeah. So Vx is 1 minus 2, so that would be a minus 1, so that should be plus 1.
This is 1, so
Yeah. Could be. I'll just post the solutions and then again, and then see the errors. And then I'll have to regrade those that got marked wrong.
this one was taken by rock show, or no?
Yeah, this was 2C, yeah, so that was rock shots.
Okay.
Yeah, so that didn't get caught. Okay.
Yeah, I've got a few others that will need it.
I do love using like my other stuff. It's like you're gonna go wrong, and there's so many things you have to check. Oh yeah, teacher canceled class and I was
It's 2J.
All right, so solution for this should be that VTH is 3.33 EJ to the 33.69 degrees. Yay, nay, getting some yeses, okay. The ZTH should be 1.154-ish minus 0.23J. Is that yes? Same? I'm seeing some yeses. Okay. All right, if you didn't get those, do review these solutions and make sure that you can get those answers. Any questions? If you didn't get the answer, any questions? Yes.
For ETH, did you just take like the C method and then just turn that into like the E form of
So I did V2 is what I called that node at C, and that's equal to VTH. Is that what you were asking?
Yeah.
Yep. Yeah. So V2, whatever node voltage you call that one, will be your VTH, correct? So yes, I use that. Any other questions, comments? Okay, questions about the ZTH? So what will this look like? It will be what? What's this one? Resistor. What's this one? Capacitor. So 0.23 J and a 1.154. And then VTH is, what was it again, 3.33. 33.69. Yeah.
Is it always a capacitor, or are there times where it can be the inductor?
So if it's a plus, it will be an inductor. And the negative is because it's a capacitor. So negative and plus will determine what element that will actually take in that form. So this negative or positive determines capacitor or inductor. The capacitor will always be the negative and the inductor will be the positive of that. And then a resistor is the only element that's a real one, so that will always be a resistor if you have a real component. So you won't have a resistance if that ends up being 0. All right, any questions? Yes. In where? The I is the J. So I did 1/3 plus 1/3, and then my Z4 is where my J's are. So I used a temporary variable there to calculate that one. So that one is the one that has the capacitor 1 over minus 2J, and then I just combined these two together for 6J as a summation. Does that make sense? Other questions, comments? Okay. All right. To determine I of t here, how are we going to determine I of t? What do we know? Do we know VS? We know VS, right? What is VS? 12, correct. Do we know V1? We do. V1 is this. So I can use those values. So we have 12 minus 6.4615 minus 3.6923 And that's all divided by 3. So this would be that answer in polar form or in rectangular form. Which form do we want it to be in? Which form? I'm trying to find I of t. So this is just going to be the phasor I is 1.846 plus 1.23 j, or 2.218 e. Is this degrees? This looks like it's in there we go, 33.7 degrees. J. Okay, so there's our I. How do we get I of t? Anyone? Go for it.
Convert it to calculate.
Okay, and how do we convert it?
So that'd be 2.218 cosine, I believe our frequency was 10 to the 4th, yep.
Yep.
T. Plus 33.7 degrees.
Correct. So we use the angle and the magnitude, and then we use the original frequency. Okay? So this would be our I of t. All right. Any questions? Okay. All right, so for this one, find IL of t. And note that you have, for the voltage source on the left, you have a DC and an AC signal there. So you're going to have to do both solutions.
I don't know a solution. I have to calculate this.
With have you gone over how to solve with the DC offset? It's just separate? Okay.
Yeah, so you short out the AC, and then you short out the AC, and then you leave just the DC,
Oh, okay. As a source.
and then you put a wire for the inductors because there's no frequency, and an open for the frequency. So there will just be 9 divided by 20 will be the DC part of it.
As the superposition.
Yep.
It's
Positive or negative 90 converting sine to cosine?
Do you remember that?
No, I have it written down for that reason. So it's, if it's plus sine, then it goes to cosine minus 90.
Cosine minus.
Yeah, they're opposite.
Oh, okay. So it has to be, it's depending on the positivity of the sign.
Yeah.
Okay.
So I guess we always want it to be a negative j, essentially. No? I guess that would be a negative j.
So if it's positive, it should be negative. If it's negative sign, that's positive.
It's 50J, 10J.
Yeah, that's why we got it. Yeah, when I come with this, yeah, like, this comes with negative, that's your figure for reason. Now you know about that. This is a good.
Okay. Like, where's my- Okay, so for the DC solution of this, you're going to zero out the AC, so that then will put, the source goes to 0 for this one. There's no DC component. So this is a wire, and then the 9 volts is going to stay in the DC side, and the AC portion of it goes to 0. So AC goes to 0 for both of these. And then your component now, when you're looking at the DC portion, that frequency is 0. What?
Is that a different problem?
No, it's the same one.
Oh.
I just removed the values. And then because of this, J omega L is going to be 0, so it's going to look like a wire. And 1 over 0 is going to look like infinity, and so this becomes an open, and this becomes the wire. We're solving for this. IL, yeah. And so IL in this case is going to just be 9 divided by 20. And that's because ground is here. So questions on the DC portion? Okay. For AC, you're going to convert these. So this ends up being minus 50J. And then this one is 10J. This gets to be, so this 4 sine goes to 4 cosine, 377T minus 90 degrees. So this is going to be 4 EJ minus 90, which can also be written in J form as minus 4J. So if you convert the 4E minus J90 into rectangular, that's a minus 4J. This was minus 50 and 10. And then this is going to be, I call this Vx, so Vx minus 9 over 20. This is Vx over 10J. And this one is Vx minus a minus 4J over minus 50J plus 30. so summing these. This gives us a VX. Let's see what VX is. Okay, where's my? Okay, I just had this here. It's bizarre. There we go. Oh, I don't have a number for VX, but IL. Go. IL is going to be VX over 10J, and that ends up being a 0.64 E to the minus J 37.66 degrees. And so converting this to time is 0.64 cosine 3677t minus 37.66 degrees. So those are your answers there. All right, questions? Yes. Here, wait, shh. Oh, question. Sorry, what is that? Oh, yes, sorry, thank you. So yes, note that this was the DC portion of this. The AC is just 12.
What about the other permission that was? Also, I found the lab on the registration.
Okay, good. Permission code for,
The daily quiz.
oh, it's called complex?
Just all lowercase.
All lowercase, yeah, complex. All right, so that should be the same answer. I just had the equation incorrect there for the AC portion. Yeah. So the DC portion here goes to 0.